All right. We're going to start working towards kind of the old school way of actually how they would find this area before we give you the shortcut. So we're going to determine the area of the region enclosed by the graphs of y equals x squared, the x-axis, x equals 0, and x equals 1. So that's a lot of information thrown at you right away. So probably best to get kind of some of that written in there, because we know what y equals x squared is. That's a parabola that opens up, right? It goes through 0, 0, 1, 1, and various other points. But we know the x-axis is also one of them, and then we know that it's x equals 0 and x equals 1. So before I put it on the official graph, I'm just going to kind of get an idea what this looks like. We got the parabola, right? We've got, obviously, that one right there is the x-axis. We've got x equals 0, which is probably a line I should put in a different color. X equals 0 and x equals 1. So in other words, they want to find that, correct? That's what they're looking for, that particular area. Okay, because x equals 1 stops me here, or x equals 0 stops me there. X equals 1 stops me there. And I have x-axis in the parabola. So that's what we're looking for. So now that I know kind of, we know it's 0, 0, 1, 1. Kind of cuts through like that. Because here would be x equals 1, right? And so in other words, this is what they would like me to find as accurately as possible. And they've given me a variety of rectangles to use: 4, 8, and 100. And then they say, actually, determine the answer, which we will. We should be able to get a pretty good guesstimate. I don't know if I'll keep this up here. I might erase it once we're done. But we know that this is 1 and that's 1, right? So if I had the whole, basically, square here, it'd be 1 square unit, correct? So this is probably a little bit less than a half of a square unit, right? Maybe a third or somewhere around there, right? So we should expect our answer to be somewhere around that. Okay. Any questions so far on the graph? How I figured out where the area was that we're trying to find? Okay. Well, what we're going to do is get going. Now, let's face it, this one for 4 rectangles, we could actually draw those in and do that one just in general by hand, correct? But then do we really want to do 8 by hand? Yeah, probably not. Do we want to do 100 by hand?
Yes.
Yeah, well, you go ahead and do it if you really want to, but I'm not going to. What I'm going to do is, remember that sigma notation we came up with? It started with all those i's in it, and then all of a sudden, once we substituted things in, all that was left was n's, right? And n stood for the number of rectangles you wanted to put in. So if I could do that here, I could get down to the end, and I could substitute 4 in for n, get an answer. Substitute 8 in for n, get the answer, and substitute 100 in for n, and get the answer. So I see a couple of you already went into your folders and got that little slip of paper that has the little shortcuts for sigma. Probably not a bad idea. Okay. So now the first thing we got to do is, well, what am I actually going to use sigma for? Well, we know we're going to put a bunch of rectangles in here, right? And if we're going to find areas of rectangles, what are 2 very important measurements? Yeah, the height and the width, right? Agreed? Okay. So we need to figure out how would I represent the width, and how am I going to represent the height? Ooh, somebody had a good idea on width. I heard b minus a. Okay. But wait a minute, what did we do before? For example, if I knew there was 4 rectangles, we would do b minus a divided by 4, and that would tell me how wide each one should be, right? If there was 8, we would do b minus a and divide by 8. If it was 100, we'd be b minus a and divide by 100. So it's really b minus a divided by n, right? Isn't that how wide each one would be, no matter which of these we use? Now, the reason we're doing this together is this is very difficult for a lot of people. We're taking a very specific problem and we're making it very general. We're doing it algebraically, you know, and basically no numbers until we get to the very end. Okay. So in this problem, do we know a and b based on our problem? Because it's 0 to 1, correct? So in other words, it would be 1 minus 0 over n, otherwise known as 1 over n, right? So you agreeing with me that that's our width? And that's going to be the width every time, correct? What have we done with things like that that happen every time? in our math, what have we done? Especially on the worksheet you did for the other day. Like we had a fourth happen. Every width was a fourth. So instead of writing it in every time, we kind of factored it out, right? Or it wasn't like 2/5 one of them or something like that, right? We factored it out. So that's going to be the same thing we're going to do here. A lot of times people struggle with finding the height. Okay, so here I'm going to give you some guidelines. What I always do to figure out the height is I say, all right, where's this thing starting at? Or in other words, what's A? A is 0, right? I'm starting at 0, agreed? Plus. Do you agree I'm going to add some amount to that? So for example, if I'm trying to find this rectangle over here, I would have to add that amount, agreed? You with me on that? And then to find the next one over, I'd have to add the width again. To find the next one over, I'd have to add the width again of the rectangle, right? I would just have to keep adding the width in to find out that x value, agreed? As I went across, you with me on that? So we're really adding, well, in this case, what am I adding? How wide is it? 1 over n. Do I know how many times I'm going to have to do that? Not necessarily n times, you're on the right track. Here's what we're actually going to put into sigma. I'm going to do that. Now you can use whatever letter you want. We're going to use I, because that's what we had in the notes the other day. Now this isn't quite the height, but we're working towards it. Because notice when I was drawing this in, was I going up for height? When I was drawing these red lines in? No, I kept saying, keep going over, right? So this gives me the x value that I need. So how am I going to figure out the actual height at all of those? For example, if I was here at a half, how would you figure out how tall that was? Put it in what? X squared. What if I was over here at 3/4 and I wanted to find the height? How would I figure that out? Put it in the function. What if I was at the very first one? What would I do? Put it in the... And what represents every spot I got to stop? This is representing every x value I need to stop at. Okay, and how did I figure that out again? Start. How much do I got to go up by? That's where sigma is going to be. That's how sigma is going to come in, right? It's not that hard, right? Once you kind of do it, once you do this a couple times, it actually gets a little easier. But it's very abstract, so I understand that there may be some struggles. So what I have to do is, let's face it, what is 0 plus 1 over n times I? Isn't that just I over n? Like simplified? You with me on that? But you see how I showed you where it came from, so hopefully you can reproduce it. So f of I over n is going to be my height. Again, you told me when I was at a half, it'd be whatever I got when I put in the function. When I'm at 3/4, whatever I got when I put it in the function. This is going to be a really colorful picture by the time I'm done, because I just keep tracing over the same stuff. All right. Well, what is that? Well, let's put I over n in. Put it in here. So it's I squared over n squared. Now we're going to take a slight break. See if there's any questions so far. I think we're really going to find the questions when you try and help me on the second one. I think that's when we're really going to find out what stuff made sense and what stuff didn't. Does anybody want to take a break and write some notes in as to where the stuff's coming from? I know the 0 plus, this thing right here has seemed to help students in the past, showing them where that comes from. Otherwise, that seems like I just made that up. I over n. Yeah, I just make it up. Yes. Oh, I is going to come in because we have to keep reproducing this lots of times, correct? We know in one of the times we're going to reproduce it 4 times, one times 8, one other times 100. The I comes in for when we're going to put it into sigma to add it up for us. That's why we had to put that in there. And what's the one thing that's going to keep changing is how far over I have to go, right? That's the thing that's going to keep moving, right? Okay. So here we go. Let's give this a try. Here's sigma. Wait a minute, what are we going to add up? We're going to add up the area of these rectangles, right? How do you take the area of a rectangle? Width times height. With me on that? Okay. And we're going to use I. Why are we going to use I? Because that's the variable we chose. If you like J or K or whatever one you're going to put in there, those are the ones you got to put. L, whatever, you know. That's what you're going to use. And we're going to start at 1. We're going to go to n. Now the reason we choose 1 and n, take a look at your little slip of paper. Those all go from 1 to n, right? So that's why we're going to use that one. So what do we really want to add up? These areas. So let's add up these areas. What's the width? Right, that's the width. Isn't that what you told me it was over here in red? Times the height, but the height change, the height changes every time. Width's the same every time, right? But the height changes. And so our best representation of that is I squared over n squared. Width times height, and a bunch of them added up, right? How many? Don't know yet. But when we get done, we're going to do 4, 8, and 100. But basically, once we get done, could I ask you for any number of rectangles? Yes. No, the first one's 1 over n, and the second one's I squared over n. Yep. So wait a minute. What did we say the other day? The only thing that needs to stay in sigma is whatever you're substituting things in for, right? So we've got this 1 over n. Does that need to stay in there? Am I really going to replace that n with anything right now? No. And really, what do I want to do? I want to get rid of the i's, right? Okay. So if I could get rid of the i's, we're going to do that by actually leaving them in there because we have that little slip of paper that you have that tells you what that is. So this 1 over n, get that thing out of there. Is there anything else I can take out? Yeah, isn't there really like a 1 over n squared in there as well? See that? So can I really take out 1 over n to the third? Everybody see where n to the third would be in the denominator? Times, and hang with me, this is old school. What's left inside then? I squared. Yeah, and you might not like this, but this will definitely guarantee you appreciate the shortcut. All right. We're almost there. I know you don't think we are. Sorry for the interruption there. I had a little phone call for those that couldn't figure out what just happened. We're almost there. Because now, take a look at your little slip of paper. Do I have something that I can replace that with? I do. Hey, what about this 1 over n to the third, though? That's got to hang out there, right? So we've got this 1 over n to the third. Now, can somebody tell me what to replace? So basically, the thing you're going to write down is going to sum this thing up for me. Awesome. So look at your little slip of paper. And what is the summation from 1 to n for I squared? It is n times n. It should be plus 1, right? Plus 1? Yep. All over 2. Whoa. Did I? Oh, am I writing the wrong one now? That's why. Somebody's messing with me, that's all there is. Well, that too. N times n plus 1 times 2n plus 1 all over 6. Whoop. Now, at this point, we have to make a decision as to whether or not we want to multiply that out. I think we should. And then I would definitely recommend that once we multiply out this part right here, you write it on your cheat sheet what it is multiplied out. Is that a good plan? Let's do it. You are allowed to write it on your little sheet of paper. So if I do this as n squared plus n, are we in agreement with that? And then it's also times 2n plus 1. That's a plus 1. I'm not going to worry about the denominator just yet. Let's worry about the numerator. 2n to the third. Again, this is a 1, remember. Plus n squared plus 2n squared plus n. Now you're starting to see why you have a full sheet of paper to do the calculus. So 2n to the third plus 3n squared plus n is your numerator, right? I'll give you a second to catch up. I see a lot of you writing feverishly. I was really kind of hoping one of you would say something prior to that, but that's all right. And this is all over what? All over 6 n to the third. No. I was just hoping somebody would have said, why don't you cancel that n with one of those? It could be. Yeah, then you wouldn't have that multiplication, I suppose. But again, that would probably have been the quicker way. But now you do have the multiplication for I squared, though, so that's good. All right, now what do we got to do? Well, now, what can I do? Well, I could cancel out an n on all of them. Yeah, okay. So it's 2n squared plus 3n plus... What happens if I cancel an n out of that one again? Yeah, very good. 1 all over 6n squared. Did you have to do that step? No. Will it make your numbers maybe a little easier to work with? Yeah. That just seems like an arbitrary function. For example, if somebody would walk in right now, oh, that's a nice function. They would have no idea what it represents. In this particular problem, it's going to represent the sum of all those rectangles, depending on how many I want to put in there, for the function x squared from 0 to 1. So wow, that function's actually pretty powerful. So now what we're going to do is we're going to put in 4, put in 8, put in 100, and it will give me those answers. Yes? Oh, the question was on the little slip of paper, why is it not written multiplied out? Because sometimes people do actually like it factored out, because then it can factor with other things in the problem, potentially. Yep. For example, if that n plus 1 is going to cancel out with something, we'll let it, right? Or some people like to just be able to put n in at that point and then find the answer at that point and not even worry about multiplying it out. But we're going to take the limit, so we need to see it. And that's why I chose to multiply it out. Because let's face it, couldn't I have substituted n at this step? Right? There would have been no rule against that. Okay, but what we're going to do with it next is why we kept going. Good question. So let's put in 4. So if n equals 4, again, n equaling 4 means what again? Means I used 4 rectangles. Okay, and they would happen to be, in this case, the left-handed one. But in this case, it doesn't really overly matter. So if n equals 4, I'm just going to do the math for you because I know this is something we can all do at this point, right, with a calculator. I'm not too worried about it. You would end up with 15 over 32, which is equal to 0.46875. Is that believable based on our guesstimate earlier? We knew it was less than a half, right? Probably more towards the third range. So what do you think is going to happen if I go to n equaling 8? Smaller. Okay. It is going to be 51 over 128, which is 0.3954375. And I think it actually does terminate. I'd have to check, but I think it might. And the one nobody wanted to do by hand, because who wants to draw that many rectangles in the span of 1? So from 0 to 1, that's not going to be a very wide rectangle, right? You get, oh, I don't even have the fraction on this one. You get 0.33835. Does anybody believe, based on, there's a lot of information on your sheet of paper right now, but based on that, does anybody believe they know the actual answer? What is the area underneath the curve of x squared to the x-axis from 0 to 1? Yes? 1/3. Do you have a basis for that answer? Other than the fact that I said it's probably around 1/3 somewhere earlier. Okay. What if I were to add something here? Limit as n goes to infinity, meaning put in a huge number. Put in a huge number and square it and then take it times 2. All right, that's big, right? Compared to that, is 3 times something big really doing all that much? The plus 1's doing basically nothing. Over 6 times that same huge thing that was up there, correct? Boy, have we done this before somewhere. Yes, we have. Just looking at horizontal asymptotes. And so it is 2 over 6, otherwise known as. That is actually the area underneath that curve from 0 to 1. So how many rectangles did I put in? Technically in that last one, how many rectangles did I put in? I put infinite rectangles in. That is not the shortcut. The shortcut itself is even better. The shortcut itself does not deal with sigma. But this is what the shortcut does. Now, but I do think there is so much math that is done via sigma, we have to show it to you a little bit. I would feel bad if you got to college and you saw sigma and said, what is that? Okay. So let's determine the area of the region enclosed by the graph of y equals x to the third. The x-axis, x equals 0 and x equals 2. All right, well, we're going to make an approximation using 2, 4, and 100 rectangles this time, and then we're going to determine the actual answer. Once again, I kind of like to just get a little idea of what's going on, right? X to the third, something like that, right? And it's from the x-axis, which is right down here. X equals 0 and x equals 2. So in other words, that area right there. Everybody see where that's coming from? Just a little sketch, right? Oh, hey, look, I only gave you the first quadrant. Imagine that. All right, so it's coming in like that. Whoa. Oh, you don't have anything? Really? Well, what a bummer. Sorry about that. I thought I did. And that was so horribly drawn, I can't even look at that. Look something like that. So this number over here now is 2, and that's 0. Any guesstimates this time? I'll let you draw it first, obviously. One-fourth. Well, this is 2, and this is probably 8. How did I get 8 for that side? Because that x value of 2, the y value is 8. Would you like to take back your answer of 1/4? You want 4, which is a random number, 4?
No.
Okay.
1/4 times.
Oh, 1/4 of 16. There you go. All right. So again, if I made this whole big rectangle here, the whole thing would be 16. I definitely don't have anywhere near half of that, right? You think I have near a quarter of it. And that's what somebody said about 4. Well, let's see how accurate that is. So you think something with a curve like that can be that accurate? The funny thing is I think 4 is actually correct. Okay. So let's find, what did we find first? Width?
Yeah, I guess there.
Is b minus a over n. So in this problem, can we be more accurate? Yes, we can. What's b? 2. Minus a, which is 0. Now, a lot of people kind of forget about a because a lot of times it is 0. And then all of a sudden they get to one where it goes from 1 to 2, and they're getting everything wrong because they failed to realize, oh, it only went to 1. Right? Over, well, we don't really know, right? So n. So in simplified form, our width is 2 over n this time. So you see how your width can change depending on your problem, right? But that's what it's going to be no matter what I give you for example, if I did say to give me 2 rectangles, 2 agree, each one would be 1 wide, right? If I use that formula. Again, probably the hardest for a lot of people is that. So again, put in, what I like to do is keep it simple. Figure it out. Where do I start for finding all these x values as we're going along? I start at, you always start at whatever a is, which happens to be 0. Again, if I start at 1, you see how that changes things drastically here? But I'm starting at 0. I'm going to add on a certain amount. Well, how much am I going to add on? Whatever the width is. 2 over n. Yes, we have a question. number of the... No, it's always B and A. It always goes that way. So. Yeah, you could look at it that way, the way that we're putting it up there. Yep. Yeah, good question. Somebody's saying, isn't that's pretty much just A right here then? And yeah, pretty much the way that we're doing it. But a lot of textbooks skip right past all of that, so you might not ever see that in a textbook. Okay, because they jump right to what we're going to do last. But then what we're going to do is we're going to keep letting that move over, right? Because we don't know how many times that yet. So now is that really the height? No, those are the x values, right? All the x values I'm going to need. So how am I going to find out how tall they are? We'll put it in where? The function. So I have to actually find f of, well, can this be simplified at all? Really, it's just 2i over n, right? A lot of textbooks skip right to that and completely don't tell you how they got that. And then you get to one that starts at 1, and you wonder why it's 1 plus 2i over n, and they just have no explanation for that. Okay? But that's what it actually is. Okay? And why do we put the I on it? No, it's not because it's area. It keeps it moving across, exactly. It keeps it moving from 0 to 2 in this case. So here we go. Again, we use that as our starting point because that's what we have the shortcuts for. Right? 1 to n. And what are we actually adding up? I really need you to keep a grasp of this, of what we're actually adding here. What about the rectangles? The area of the rectangle. So we're adding a bunch of widths times heights. So what's the width? Well, 2 over n, right? Times the height, which is, well, do you want me to write it as f of 2i over n, or should we put 2i over n in the function and figure out what it is? That's up to you. You want to figure out what this is first? Before we put it down here? Yeah, no, I've heard both. I'd say we probably should. So let's put 2i over n in there, right? So it's 2i over n cubed, right? Now notice, as the function gets harder, does this also get harder? Yeah. So you notice I did choose some pretty nice functions to do this with. And some nice a and b values, right? So you truly will appreciate the shortcut by the time you get to it. So it is, what, 8 I cubed over n to the third? Any strategies that we should try here? Quitting is an option, but you'll never get the answer on this one.
Already had the answer.
Well, that's true. You already have the answer because of your infinite wisdom. Oh, ouch. All right, so what should we do here? Any ideas to make this? Because let's face it, what would we like to go away right now? We want to get rid of I cubed and the sigma. It'd be great if those two things could go away. Yes. Let's take out the 2 over n because we know that always happens. Is there anything else we know is always going to happen? We know the 8's always going to happen. We know the end of the third's always going to happen. So what can I really take out? I can take out a 16 over n to the fourth out. And as the functions get more complicated, yes, there's less and less you can actually take out. Okay? But right now, if they're going to let me take all of that out of the sigma, we're going to. And basically, the only thing left in there is that. And I know these notes are long, but at least as of this year, there's no assignment today. Yet. Why would I want to do that? What would be the purpose? I can replace it. Exactly. I know exactly on that little sheet of paper that you got there. We know what that is. We got 16. Yeah, I got to give me that thing. Make sure I write down the right one this time. Oh, hey, this one's shorter than the last one, though. Now this time, if you want that multiplied out, you're going to have to do that on your own time, because I'm not going to waste my. I see something I can do that's going to save me time in the long run.
Get rid of the insert.
All right, we've got, has everybody done writing that? We've got an n squared here that I can cancel with 2 of them down there, so it's just, wow, that's really bad. That's n squared. Looks like n with a 2 on top of it. So really we've got 16 times n plus 1 squared all over 4n squared. And I'll show you maybe why I multiply things out. It's completely up to you, but at this point, this is probably the fewest number of n's you're going to get in this thing. Now would be a really good time to replace n's. Okay? And I'm going to have you do that on your own. So you have to replace it with 2, 4, and 100. And then I would also like you to tell me, what is the limit as n approaches infinity? The number of rectangles approaches infinity. It might be harder to see it in this form, okay, based on what we've done before. So go ahead and work on that. I will stop the recording, so those watching it, if you need those answers, come to me.